We've been talking about gases, specifically the ideal gas, well, the idea of an ideal gas, and what happens when you do certain things to it, like compress it or allow it to expand or heat it up, different things like that. But we also have to make sure that we talk about solids and liquids and other states of matter, because we can talk about what happens to those in the same sorts of conditions. So, just to run down the typical states of matter that we would be talking about, we have solids, which have a definite volume and a definite shape. And you can have a crystalline structure where you have a very, very rigid arrangement of the atoms and molecules that make up your solid, or you could have a more amorphous solid type deal where you have more random motion, a more random arrangement, pardon me, for how the atoms are stacked up to make up your actual material. But a specific relationship that we have to think about is how these particles are arranged in their structures, which adds internal forces to keep them into that structure. And these internal forces will pretty much resist compression to some extent or another. That's a very important point to think about with how this is different from other states of matter. So we have liquids, which have a definite volume, but they don't have any definite shape. They end up actually filling whatever container they are placed in, or spreading out all over the floor if you happen to spill it. Okay, so they will have no definite shape. But these still will have some internal forces because of how those atoms are arranged in that liquid structure. Okay? So there will still be some sorts of things that end up actually preventing compression as well. Then we have what we've been talking about, that being a gas, which has no definite volume or shape. And the particles don't really interact that much with each other, which was one of the big assumptions that we made when dealing with the ideal gas. And so you can compress this material, this state of matter, a lot, basically down to the point where you have some other effects that might take over with intermolecular forces once you get down to a certain amount of squishing. But you can, for any other scale beyond that, this is very compressible, unlike what is true for a solid or a liquid. Now, if you go beyond those typical regular states of matter, you still have plasma, which is a high temperature ionized gas. Okay, so in this high temperature ionized gas, what that means is that you have a gas, but it's been subjected to a high enough temperature or some kind of process that has stripped the electrons from the atoms. So that you have either a bunch of electrons, or you have a bunch of nuclei, or you have both together, just not combined in neutral atoms. And then you have other forces with the positive and negative charges that are on the particles, and some other different things that could end up happening with regard to their interactions that make it a different situation and have different behaviors, therefore, than just a plain old ordinary gas. Another part of this that I have to mention are two other states of matter and energy that we should mention because they're different than all of these. You cannot classify these in terms of solid, liquid, gas, or plasma because they are completely different. So if you look at down here, I have mentioned dark matter and dark energy. What dark matter is that it is some other type of matter. We don't really know what it is yet, but it is some type of matter that is not protons, neutrons. It's not what we're all made of. It's instead made of something else. And a special property about that is that it doesn't really interact with us. And it also doesn't really interact with light. But what it does do is that since it is matter, it does have mass and therefore exerts a gravitational pull. And so we can actually measure the amount of dark matter there is by looking at gravitational effects. Another thing that we can measure is some force that we see out there in the universe that is actually making the expansion of the universe go more quickly. based on what we think happened with the Big Bang, the expansion of the universe should be slowing down because the gravitational force of everything in the universe should be counteracting that expansion. Now, in 1999 it was realized that that is not the case, that instead the expansion actually is speeding up right now and not slowing down, so we think there has to be some other type of energy out in the universe that is providing a counter anti-gravity sort of effect, a repulsive effect that is pushing things apart more quickly than just the expansion by itself would. And so these two different types of matter and energy are very, very different from the other states of matter, and therefore they need to be mentioned. But it is an important point to note that dark matter and dark energy are not the same thing, even though they both say dark. The dark matter part means it doesn't interact with light. The dark energy part, the dark part of the dark energy really just means that we don't know what it is, and so we're going to call it dark, which unfortunately I think is confusing for lots of people because they think that these two things are the same thing, and they are not. They're also not black holes. The dark and the black can get confused as well. But those are the different states of matter, and we're just going to focus for now on solids and liquids, since we've been talking about gases. Since solids have a definite volume and a definite shape, there are certain things you can do to a solid to affect its shape. So we can talk about deformation of those solids in terms of two things, that being stress and strain, where stress is the force per unit area that apply to an object to change its shape, to deform it. And the strain is actually a measure of the amount of that deformation. So for relatively small stresses, the relationship goes as follows, that the stress is equal to a property of the material times its strain. So the force per area you apply to it results in your deformation, by however much that happens to be, dependent on what the material is. Therefore, how willing it is to actually deform. How much it's able to give into the force that you're applying to it. And that is called some type of elastic modulus. Okay, and there are three different types we're going to be talking about. But this is the proportionality constant that relates the stress and the strain. The higher this constant, the less your object will actually end up deforming. Okay? So if you apply a certain force here and this number is bigger, that number is going to be less. Okay, so the higher this number, the less your object is going to actually be deformed. So if we talk about elasticity of length, or deformation in length, then that gives us the idea of Young's modulus, where the force per unit area is equal to capital Y, which stands for Young's modulus, times the change in length divided by its initial change. So this is the stress you apply, this force per area. This is its a measure of its change in shape, its change in length divided by the initial length. That ratio there is a measure of the strain, since it's a change, times the elastic modulus of the material, that being Young's modulus. So, say for example, I have this solid right here, even though technically it's a slinky and therefore slightly different, this is still going to be able to apply. So I can apply a force per area, pulling on this, and I change its length. Okay? this would obviously have a very low value for capital Y since I change its length quite a lot. Okay, but that's the idea here. You apply some force per unit area, this being the cross-sectional area of our solid involved here, which results in a strain, results in a change in length divided by the initial length. Well, it results in a change in length, and you measure that by the change in length divided by the initial length. So that's the change in length. If you go into 2 dimensions, we'll talk more about the change in shape, and that would be the shear modulus, where now the force per unit area is equal to, let me write this down and I'll explain it first, and then explain it afterwards, the shape times, not the shape, the shear modulus, capital S for the shear modulus, times delta x over h. So what is delta x and what is h? Delta x would be the amount horizontally the object moves, and h should be the height of the object. So what do I mean by this? So I hold one end of my object fixed, and I apply a force to another part of it. And the object will change shape because of that. And it will shift over by an amount delta x. So that's where that delta x comes from. And that also depends on how high the object is. If I'm only looking at half the slinky, then the amount of deformation is going to be different than if I'm looking at the whole slinky and applying the force. Okay? So it depends on the height of the object, and it depends on, and then you have the resulting horizontal movement, which depends on how much force per cross-sectional area you actually end up giving it. So actually, in this case, the force is parallel to the cross-sectional area, which is different than other cases we're usually thinking about. But that's the shear. You end up distorting the shape of the object by applying a force in a specific place and holding the other part of it fixed. So that's 1 dimension, 2 dimension, this would be 3 dimensions, and that would be looking at how the volume would be affected by this, and this is called the bulk modulus. And this is subjecting some solid object, or something else, potentially, to a uniform pressure on all sides. Like, say, for example, placing something inside a container of water. Okay? If I had a ball, or, well, I don't have a ball, but if I can think about it this way, and I apply a pressure to all sides, there's a possibility that this could actually compress. Okay? If you think about a stress ball, that's something I mentioned in class, then if you squish the stress ball, it's going to decrease in volume because of the pressure that you've applied. Okay? And so that's what we're going to be thinking about here, that some force per area spread over the surface of your object that is being applied uniformly to the entire object is going to be equal to something called the bulk modulus, again, instead of shear modulus, or Young's modulus being the property of the material to respond to this, times the change in volume divided by the initial volume. Okay. Now, the negative is there because when you apply the pressure, you're going to compress it. And so the delta V is going to be negative, because delta means final minus initial, and the final volume is going to be smaller than the initial volume, so this is going to be negative. So in order for this to work out, this negative has to be there. Okay. So it's a result of the fact that the more pressure you apply, the smaller the volume gets, and therefore the delta V there is going to be negative. And this all has to do with just the individual properties of each solid to know how those atoms and molecules can respond to those forces and still keep a shape and not come ripped apart. So these obviously will break down if you actually end up breaking apart the object or squishing it beyond repair. Okay. But these are what we can think about with regard to if we wanted to deform a solid.